Hey everyone, I am Miss Hu, your physics teacher. This video lesson will be covering the concept of liquid pressure, where we will learn about the formula for liquid pressure, solving questions involving liquid pressure, as well as applications of liquid pressure in real life. Now, this video will only be covering the theoretical understanding of liquid pressure. I do have other videos which show practical demonstrations of liquid pressure, which you can also do at home. For this video, we're going to cover what we need in order to answer the questions in our examinations, especially for SPM and IGCSE Physics. Now, before we go into the formula for liquid pressure, first of all, let's have a clearer understanding of liquid pressure. Now, let's look at this glass apparatus. You can see that this entire thing is actually one piece. I don't have this in real life, which is why I'm using other people's pictures. So what we're looking at on this slide here is a picture of a glass apparatus where all of these vertical tubes are connected to the same horizontal tube. You can see this all actually one piece. So this is one horizontal glass tube with 4 vertical tubes on top with different shapes and sizes. This tube has some kind of cone shape in the middle. This is a thin diameter. This is a thick diameter, while this tube is at a slant. When you fill up this tube with water, regardless of the shapes and sizes of the vertical tubes, the water all come up to the same level. This of course only works when all of them have open tubes at the top and are all connected to the same horizontal tube. Although there are different vertical tubes with different openings over here, because all of them are connected, what happens is that all the water in these tubes are pushing against each other, trying to find pressure equilibrium. Regardless of the shape and size of the vertical tubes, they will all come up to the same level like this. So people who don't understand liquid pressure, or maybe have never seen how liquid balances itself out in real life, may expect that the level of waters to be different in all these different shapes and sizes. It doesn't matter what's happening on the vertical tubes, as long as they're all connected to the same horizontal tube, they will all come up to the same level. So in the next couple of slides, I'm going to show you some pictures of other similar glass vessels as well. So in this diagram here, we have 4 vertical tubes all connected to the same horizontal tube, and similar to the previous photo, you can see that regardless of the shapes and sizes, the water all come up to the same level. Again, because the liquids are trying to achieve pressure equilibrium. This can also be seen in this case. Again, 4 vertical tubes connected to the same horizontal tube. Regardless of the shapes and sizes, all the water come up to the same level. Remember that this only works when all these tubes are open to the same atmosphere, and the tubes have to be large enough. Just a note, this does not work when you use a capillary tube. We will talk about capillary tubes in a separate video. For now, we're just going to focus on the concept of liquid pressure. So what do these apparatus prove? We'll look at the formula shortly, but first let's start off with the general pressure formula. As you should have learned by now, pressure is defined as force per unit area. The formula for pressure is force divided by area, or you can write P equals F over A in symbol form. The SI unit for pressure is Pascal. I'm going to write over here. The short form for Pascal is written as PA. So PA stands for Pascal. But if you look at the formula, you can see that you can also write it as Newton per meter squared, where Newton is the unit for force and meter squared is the unit for area. Sometimes you might come across questions where the area is given to you in centimeter squared instead. So you can also write the unit as Newton per centimeter squared. One thing you should note though is that Pascal is equivalent to Newton per meter squared. There are actually many more units for pressure, but we'll just write only these 3 because these are the 3 most common units used in your examinations. There's more to learn about pressure. If you'd like to find out more, please watch my video on pressure. For now, let's focus on liquid pressure. So what you should know is that this is the general formula for pressure, and this formula can be used in all cases, whether solids, liquids, or gases. But Having said that, for liquid pressure, there is a much more specialized formula because of the factors which affect liquid pressure, as we saw in the earlier pictures. The formula that you should know for liquid pressure is rho g h, where rho is the density of the liquid which we are calculating the pressure of. For example, if you're calculating the pressure of water, you use density of water. Please take note, students, that this is rho, not P. A lot of my students like to say, oh, pressure is PGH. P is pressure. This is not P. This is the Greek letter rho, which is normally used as the symbol to represent density. The unit for the density of liquid used in your calculations must be in SI units, which means that it must be kilogram per meter cube. You cannot use gram per centimeter cube. If the question gives you the density in gram per centimeter cube, you need to convert it into kilogram per meter cube. If you don't know how to convert it, please watch my video on the unit conversions. G, of course, is the standard symbol for gravitational acceleration. The unit for gravitational acceleration is meters per second squared. On Earth, this is a fixed value. If you are studying IGCSE, then the value you use for G is 9.8 meters per second squared. If you're studying SPM or A levels, then this value is 9.81 meters per second squared. So depending on which syllabus you're studying, you need to use the value of G appropriate to your syllabus. Now for H. If you refer to the older textbooks, many of them would say that H represents height. You're learning this now and you have to remember this. H is not height. H is depth. Why not height? We'll look at it on the next slide. For now, just remember H is depth. Why haven't we changed this to D? Because the formula for liquid pressure has always been expressed as rho GH for years, and we just want to keep it that way to make it easier for everyone. Just remember that H represents depth and not height. By the way, if you rewrote this into H rho G, that's perfectly fine as long as you have all the important information in your calculation. So of course, for depth, the unit must be in SI units, which is meters. The units for liquid pressure is the same as for pressure, as we saw in the previous slide, which means that the SI unit for liquid pressure is Pascal. In order to get Pascal, you have to make sure that all the values that you use in the calculations are in SI units. Pascal is equivalent to Newton per meter squared, which is another way to express it as well. Now, we rarely use Newton per cm squared for liquid pressure. Not impossible, but we don't, because if you use the SI units this way, kilogram per meter cube, meters per second squared, and meters, all of this would give you the value equivalent to Pascal, which is why we'll keep it as Pascal, and Pascal is equivalent to Newton per meter squared. So I will not be writing Newton per cm squared on this slide. In case you're wondering, why can't we convert these numbers to cm? It's because the number then becomes far more complicated. The reason why we use SI units is because we standardize the values, making it easier for ourselves, right? So don't complicate things, keep it as Pascal and Newton per meter squared. Now, in addition to this, you should also be aware that liquid pressure can also be expressed in other units. So I've drawn a line here just to separate the different types of units. You can also express liquid pressure in liquid form, meaning you can write this as meters H2O. So meters H2O means that it's equivalent to a certain depth of water. For example, if you write 10 mH2O, that means that the pressure is equivalent to 10 meters of water that is being exerted. So for example, if you wrote 10 mH2O, that means the pressure exerted is equivalent to 10 meters deep of water pressure. Besides water, another common one is in mercury. So sometimes you'll see CmHg. So CmHg means it's equivalent to a certain depth of centimeters of mercury. Now, meters H2O and centimeters mercury is more commonly seen in atmospheric pressure. So if you want to know more about these units, I'll cover that in another video because that's usually covered more in atmospheric and gas pressure. For now, we're going to focus on liquid pressure in this video. Usually when it comes to the units of liquid pressure, these are the only two liquids that we work with. Why don't we use other liquids? It's because for water, the density of water is a fixed value at 1,000 kilograms per meter cube, while mercury is roughly about 13,590 kilograms per meter cube. Are there other liquids? Yes, but other liquids may not have the same standard density. For example, if you say oil, there's many different kinds of oil. So which oil are you referring to? If you say alcohol, also there are many different kinds of alcohols. So all of them have different densities. Salt water also depends on the concentration of salt, which means there could also be different densities. So that's why normally we don't use other random liquids. These are the only two fixed liquids that we like to use because the densities are fixed and easy to work with. Now that we have the formula for liquid pressure, you must remember that the factors which affect liquid pressure are only these three variables. That means that liquid pressure is only affected by the density of the liquid, the gravitational acceleration, and the depth of the liquid. Unlike solid pressure, liquid pressure does not depend on the volume or the area where the liquid is acting on. It only depends on these three factors. Let's look at this picture to show you as proof. So in this picture, we have three different containers filled up with the same type of liquid. So they've colored the liquid to be the same color here just to visually remind you that they're all the same liquid. Now, you can see that each of these containers is resting on a base plate, and this base plate is actually measuring the pressure that's being exerted. You can see that there are pressure gauges attached to each of these base plates. From this diagram, we can observe that all three pressure gauges are showing us the exact same values. Regardless of whatever volume the liquid is, whatever size or shape of the containers are, all of them have the same liquid. All of the containers have been filled up to the same height, and therefore all of them are exerting the same amount of pressure. So this picture proves to us that liquid pressure does not depend on the volume of the liquid or the area of the container where the liquid is acting. So liquid pressure behaves very differently from solid pressure. Before I move on, let me address why H represents depth and not height. So say we have water in a measuring cylinder as shown on this slide. You could be asked to measure the pressure of water acting upon this point here, which I'll label as point P. You could be given several values. For example, you could be given D1 or D2. So when we say height, most people, when they think of height, they think of a measurement from ground up. So if they were then required to calculate liquid pressure, they'll think, oh, height, they will automatically take the value of D1 because to them, this is height. Because we measure height from the ground upwards. But you must remember, liquid pressure is caused by the weight of the liquid pressing downwards. So the pressure acting upon point P is not the water that's underneath P, but the water that's above P. So that's why we say depth, because when we use the term depth, we tend to think of surface downwards. So that means that D1 would be the correct value to use in the equation because the pressure acting upon P is caused by the water above P. So that's why we have switched the value of H to become depth, not height. Years ago, when I was teaching this concept where we kept talking about H as height, I had many students who kept using the value of D2 to calculate the pressure of P because they kept thinking of height. Yes, I'm that old. So this is why H represents depth and not height. We just keep the symbol H for continuity because it's the same formula regardless of what the name is, as long as you understand how to use the correct values. And now, let's go into how the formula of liquid pressure was derived. So this is for those of you who are really curious as to what the relationship is between the general pressure formula and liquid pressure. Because I know earlier I did say that the general pressure formula could be used for liquid pressure as well. So yes, they're related, but when calculating liquid pressure, we only use P equals rho GH. So just to show you the relationship. Now, let's start off first with the general pressure formula, which is P equals F over A. Now, one thing you need to understand about liquid pressure is that the way a liquid exerts pressure is very different from the way solids exert pressure. And because solids, the particles are in fixed positions, the weight of the object is distributed over the area. That's why for the same weight, a larger area would have lower pressure, while a smaller area would have greater pressure. For liquids, however, because they can flow, that means the particles are moving, the way the liquid exerts pressure is very different. So the liquid tends to exert pressure only above its own point. So a lot of people would think, oh, the entire volume is spread out over the area. No, the pressure of the liquid only acts upon one point. That means the pressure at this point is only affected by the liquid that's directly above it. The point next to it, it's by the liquid above it. So that's why area doesn't play a role. But anyway, let's look at how the formula is derived. So the pressure exerted by a liquid does depend on its weight, which means that we can rewrite this formula to become W over A, where W is the weight of the liquid. Weight, as we know, is mass times gravitational acceleration, and we'll keep the area as A. Now we're going to relate the liquid to weight. We know that density, which is rho, is equal to mass divided by volume. So I'm going to rewrite mass as rho times V. So if we take rho V and substitute into G, we will have rho V G divided by A. Based on this cylinder, we know that volume can be calculated as area times height, where h is the height of the liquid, or depth in this case. So we're going to substitute V equals AH now into this equation. I'm going to write it on the side here because otherwise I'll run out of space. So that means this will give us rho AHG divided by A. We cut A, that's how you get rho HG, or H rho G, or rho GH, which all come up to the same thing. So that's how the formula for liquid pressure was derived. Now, let's look at an example on how to use this liquid pressure formula. So we have a question here where we need to calculate the pressure at point P given that the density of water is 1000 kilogram per meter cube. So we're given two values over here. We've got 12 centimeters measured from the surface of the water to point P and 8 centimeters from the bottom of the cylinder to point P. We know that we need to use the formula of rho GH. So I'm going to write it over here. P equals rho GH. Now, let's recall which value of h should we use. Should we use 12 centimeters or 8 centimeters? That's right. Remember that h is depth. So we're going to use a value of 12 centimeters in h. Now for the purposes of this video, because SPM and IGCSE both use different values of g, I'm going to do this calculation 2 times. I'm going to solve this for IGCSE first, where the value of g is given as 9.8 meters per second squared. So given that rho is 1000 kilogram per meter cube, g is 9.8 and h is 12 centimeters. We don't write h as 12 because remember, you must write it in meters. So we need to convert 12 centimeters to meters. And that's where we put in the value of 0.12. So this would give us a value of 1176 pascals. But for IGCSE, we like to write to 2 or 3 significant figures with a preference for 2. So you can round this up to 1200 pascals. Now for SPM, we use the value of G as 9.81 meters per second squared. The formula is of course the same, P equals rho GH. The substitution of values are also the same. Rho, which is the density of water, is still 1000 kilogram per meter cube. But G is 9.81 for SPM. H, of course, is 0.12 meters. Remember, you don't write in centimeters, you write in meters. And the value you get will be almost the same. You will get 1177.2 Pascal. In SPM, it's okay to write to this value. You don't have to write it to a specific number of significant figures. So this is a very simple example of how to use the liquid pressure formula. This question is really simple though. You only need to calculate the liquid pressure. Sometimes they will give you a situation where you're required to calculate the total pressure. So when you see the term total pressure, you must understand that there's not only liquid pressure, there's also atmospheric pressure. So for example, this fish is underwater. We know there's pressure acting on the fish, obviously from the liquid that's above the fish. But remember that gases can also exert pressure. So because there's gas in the atmosphere, the pressure exerted by the gas in the atmosphere is known as atmospheric pressure. There's atmospheric pressure pressing on the surface of the liquid. So the total pressure acting on the fish is not only from the liquid, but also from the atmosphere. So this is the atmospheric pressure, which I'll write just here as ATM, and this is the liquid pressure, which I'll write here as LIQ. So total pressure acting on an object that's underwater is the sum of the liquid pressure and the atmospheric pressure as shown on this slide. And now let's look at how to solve a question involving total pressure. So this question is asking us to calculate the total pressure acting on a fish that is 5 meters under the surface of water. We're given the atmospheric pressure of 100 kilopascals and the density of water is 1000 kilogram per meter cube. To solve this question, all we need to do is take the sum of the atmospheric pressure and the water pressure that's acting on the fish. I'm going to solve this for both IGCSE and SPM. And again, there's a difference in the number because the value of G is different for both syllabi. We're going to start off first with IGCSE. So I'm going to write out the working so that you can solve it together with me. We know that the total pressure is the sum of the atmospheric pressure. I'm going to write ATM here for short, plus the water pressure. Atmospheric pressure is given at 100 kilopascals, and we're going to convert that to pascals. That means the value is 100,000 pascals. The water pressure formula is rho GH. So I'm going to just write rho GH here to substitute water pressure. Now we're going to sub in the values of rho GH. So rho is the density of water, which is 1000 kilogram per meter cube. G is 9.8 meters per second squared, while H is 5 meters because the fish is 5 meters underwater. So now all we need to do is total up the number. I'm going to break this down step by step so that you can follow me in terms of the working. So 100,000 plus 49,000 pascals. Adding that together, you will get 149,000 pascals. Now you can leave the number like this because remember, for IGCSE, they prefer us to write the values in 2 to 3 significant figures. But if you want to write it to 2 significant figures, that's fine as well, which means it'll be 150,000 pascals. It's 2 significant figures. Now let's look at how to solve this question, but for SPM. Solving this for SPM is actually exactly the same. The only difference is that the value of G is 9.81. I'm still going to start this from the beginning so that those of you who are taking SPM can follow the working. So total pressure is the sum of the atmospheric pressure, I'm going to write ATM here for short, plus the water pressure. 100 kilopascals is actually 100,000 pascals, so I'm going to write that out in pascals. The formula for water pressure is rho GH. We need to calculate this out. So now we're going to sub in the values for rho GH. So rho is the density of water, which is 1000 kilogram per meter cube. G is 9.81 meters per second squared. And H is 5 meters, which is the depth of the fish that's under the surface of the water. So solving this, I'm going to solve this step by step so that you can follow the working. So we will get 100,000 plus 49,050. So now when we add the numbers together, we will get 149,050 pascal. You can leave the number like this for SPM. Now, just extending a little bit more for SPM, sometimes you can express the answer in a unit other than pascals. So now let's try to solve the question using different units. The exact same question, we have a fish that's 5 meters under the surface of water, but this time the question doesn't give us a density of water, and they give us atmospheric pressure as 10 meters water instead. So in this case, how do we solve the question? So we know that the fish is 5 meters underwater, and they told us the atmospheric pressure is 10 meters water. 10 meters water, by the way, is equivalent to 10 meters H2O. Sometimes they might write the value as 10 meters water, sometimes they write it at 10 meters H2O. They're actually the same thing. So what is 10 meters water? Meters water or meters H2O is actually the unit of pressure. So that means the atmospheric pressure, which is the pressure caused by the air in the atmosphere around us, is equivalent to 10 meters of water pressing down on that particular point. Now the fish is 5 meters underwater. The water pressure acting on the fish is equal to 5 meters of water. If the fish was at the surface of the water, there will be no water pressure, but the fish would be experiencing atmospheric pressure, which feels as if it's equal to 10 meters of water. So, long story short, meters water is basically a unit of pressure. So we know that total pressure is equal to the atmospheric pressure. Again, I'm just going to write it as ATM for short, plus the water pressure. Atmospheric pressure is given as 10 meters water. And water pressure basically is 5 meters worth of water. That means it's equals to 5 meters water. So the total pressure is 15 meters water. And we can write it this way because the unit is meters water for both. Instead of writing 15 meters water, you can also write it as 15 meters H2O. Writing it this way is also accepted. Now, a possible extension of this question is you have to solve the question using meters H2O first, and then you need to convert this value into pascals. So they would give you the density of water this time. So now that we know that the total pressure is 15 meters water, so I'll write here 15 meters H2O, we can convert this value into Pascal by using rho GH. Why? Because if you look at this unit, you actually have the depth as well as the density of the liquid. The depth of H is actually 15 meters and H2O is the liquid. And if you know the liquid is water, you just need to use the density of water to substitute inside rho. So given that the density of water is 1,000 kilogram per meter cube, G will take it as 9.81 because this is more of an SPM question. And H, of course, is 15. So solving this, you would get 147,150 Pascal. Now, by right, you should expect to get the same number as the number that we solved earlier. But you might find, hey, it's a little bit different. And the reason why it's different is because this time we've used the value of G as 9.81. Earlier, the atmospheric pressure was rounded to 100,000 Pascal. So it's not really 100,000, it's actually a little bit less than that. That's why we're getting a rather different number in this case. Now, which number do we use? Again, depends on the question. Did the question give you the atmospheric pressure in Pascal or in meters water? So because in this question, they've given the atmospheric pressure as meters water, to convert this into Pascal, we have to use rho GH where G is 9.81. So that's why there's a little bit of discrepancy. So if you're worried about the discrepancy, don't worry. As long as you use the formula correctly, you should get the correct answer. Now, there are other kinds of questions that you would need to be able to answer in SPM related to liquid pressure, especially involving U-tubes. However, because this can be quite long, so I've covered this in another video, which you can check out. I've put the link in the description below. For this video, we're just going to focus on some of the basic stuff you need to know for liquid pressure. And this includes the applications of liquid pressure. So the application I'm going to cover in this case is going to be an inverted hose, or basically the U-tube, we invert it. This slide is blank because I'm going to sketch this out, so you got to bear with my sketches. So if we were to take a hose and we invert it like this, you can actually use this hose to transfer liquids from one container to another. But there are caveats to this transfer. Say we've got liquid in one container, which I'm going to label here as A, and we've got an empty container B here, and we want to transfer the liquid from A to B. Now, if you do it like this, it's not going to work because there's air pressure inside that prevents the water from moving from A to B. So the only way you can transfer the water is if you had filled up the tube with water first. So then what happens here is there is a difference of pressure. There's water pressure pressing down from the tube to this point of the open mouth, but here the air pressure is not enough to prevent the water from flowing out. So what happens here is now there's an imbalance of pressure. So the water would flow out through this mouth, and as the water flows out, water from container A will continue to replace the water in a hose to transfer to B. Now, even transferring the water, there's a lot of things to consider because the water flow will stop when the levels of water are the same on both sides. So let's say the water level stops here and here, Once they reach the same level, the water flow will stop. Why? Because if you can remember what you saw earlier with the horizontal tube and the 4 vertical tubes, the water is trying to achieve pressure equilibrium. So once the water level is the same on both sides, that means the water pressure is equal, then the water flow will stop. In order to be able to keep the water flowing, we have to keep the hose on the side of B lower than the end of the hose in container A. So this is how siphons work. That's why for the siphon to work, you have to get the hose from where we want to transfer the water at a higher point compared to the end of the hose where you want the water to be transferred. So a siphon is very useful for cleaning aquariums and water tanks. As you can see this diagram, we have an aquarium where we want to transfer the water to the empty pail over here. For this to work, you need to fill up the hose full of water first, or you can suck the water out if you like. And once this hose has been filled full of water, then the imbalance in water pressure will cause the water to flow from the aquarium into the hose and out into the pail. Now the same concept here also explains how water is transferred from reservoir tanks to homes and other buildings. If you've ever seen a water tank on a very high tower in a housing area, that tank is actually holding water for the neighborhood. So this is the water reservoir or the water tank that supplies water to this area. The reason why it's elevated is so that it generates enough water pressure to transfer the water down through the pipes to the other houses. So once the water gets transferred to the house, it needs to go up into a water tank that we normally place at the roof. So for some houses, the water tanks may be outside the roof, and sometimes the water tank may be inside the house, also in the roof or attic area. So inside a house or a building, the reason why the water tanks are on the top is again to be able to create high pressure to transfer the water throughout the building. So here's a very simple diagram which I'm going to use to explain how the water is transferred from the reservoirs to homes. So here we have a water tank that's elevated compared to the rest of the houses in the neighborhood. So if we have a pipe that is connected from the reservoir to the house, the pipe needs to be able to transfer water to a water tank that's sitting on the roof of the house. So let's say the water tank is inside the house in the attic area. So if the water level in the reservoir here is higher than the water tank in the house, you don't need a pump, because even though the water tank in the house is elevated, but the water level in the reservoir is higher than the tank, so which means that the water can flow from the reservoir into the tank. The water will only stop flowing into the tank when the water level in the reservoir and the house is the same. As long as the tank is below the water level in the reservoir, water can continue to flow into the tank in this house. Now, let's say you have a house that's more elevated compared to this house. Can the water still transfer from the reservoir to this house? Yes, it can, as long as the tank in this house is at a position that is lower than the water level in the reservoir. So even though it looks like the water has to travel upwards into this tank, remember that water is looking for pressure equilibrium. So even if the water has to travel upwards, it can still move because the water pressure exerted by this reservoir is higher than the water pressure exerted by the tank. So the water can still flow down the pipe and up to the tanks in the respective houses. So remember, this only works when the water tanks are at a position that's lower than the water level in the reservoir. What if we get a situation where the tank is higher than the water level in the reservoir? So say we have a situation like this. So what's labeled here as the water tank is actually the reservoir. I'm going to rewrite here. This is the reservoir. So we have two buildings now, and you can see for the first building that's purple in color, the tank is at a position that's lower than the water level in the water tank, which means that the water can flow from the tank of the reservoir into the tank of the purple building. But if you look at the pink building, the water tank is higher than the level of water in the reservoir. So actually what's going to happen here is that the water tank from this 5-story apartment block could end up backflowing into the reservoir. So how do we prevent it from happening? You can't knock down the 5-story apartment block into a single story or 2-story block, right? So normally there has to be a valve to prevent the backflow, and you have to install a pump in order to force the water up the pipe into the water tank. So it's not that you cannot build this in real life. You can, it's just that you need to add additional things to the situation. Now, if you'd like to know more about liquid pressure and even do some practical demos at home, I do have some videos where you can study more about water pressure at home, and you can even make your own manometer. If you'd like to learn just the theory, I do have a video on manometers, and I also cover the YouTube manometer that's found in school labs. I've put the links to these videos in the description below. For now, that is all for this video. So if you found this video to be educational and helpful, do click like, hit subscribe, and let me know in the comments how you found this video to have helped you. If you would like to help me keep making free educational video lessons and lab practicals, donations are welcomed at my Ko-fi page. That's ko-fi.com/physicsrocks. For notes, quizzes, and syllabus updates, check out my website at physicsrocks.com. Do check out videos on my YouTube channel on other topics which you might find helpful. So remember, subscribe for more free physics lessons from your physics teacher, Miss Ho. Happy studying!